Daniel for the introduction. Yeah, so I'm Ramona Modroiu. I know many of you, but also many of you I don't know yet. I try to put the microphone a bit better here. Okay. My presentation today is about sharing with you a few insights that we got during a recent experiment we conducted with our research team at TU Berlin, but also with the research team at RPTU, Rheinland-Pfälzische Technische Universitat in Kaiserslautern. We came to join our forces in a large German research project called Open6G Hub, funded by the Federal Ministry of Research and Education in Germany. And yeah, we had completely different backgrounds. The research team in Kaiserslautern is mainly on AI, but for 5G towards 6G, and at TU Berlin we are on the edge, RAN, core network application layer continuum focused. At TU Berlin we are working mainly with open source projects. At in Kaiserslautern they have other setups. And we had the chance to have to be able to build several setups of a 5G private network, and then we came to build some joint demonstrators, and therefore the idea, let's see what each team can do and how we can have a nice demonstrator for real life for agriculture. I've lost my microphone. This work, the results were put in a scientific paper that was submitted and accepted to an IEEE conference that will happen in July in Italy. And I'm very happy because it's going to be in Cagliari, and I think we have somebody here in the room from Cagliari, so I can pay him a visit, to Giacomo in 1 month or so. Let's go through the paper quickly. We don't have too much time, but I'm going to give shortly the main ideas. So what was our motivation? What was the background? We will see the 2 test beds. We will see the experimental methodology that we used, the metrics that we measured, call setup time, and quality models for estimating the quality of the calls, and then several conclusions and future work directions. So our motivation was that we have a problem. We have now private 5G networks, and these private 5G networks are not carrier grade, are small networks with 100, 200, let's say 500 users. And if we want to add voice services, voice audio, multimedia services, well, IMS, that is the native 5G voice services for, that rely on, would be overkilling. So it's come with prohibitive costs, and also operating such a system is not trivial given the complexity. So we said, okay, for these use cases, for this special case, better said, let's look at pure VoIP and see if we integrate the Kamailio RTPEngine and Linphone or Versip. We get a non-3GPP IMS alternative, but it's a growing relevance because it comes with reduced cost and architectural simplicity. you can deploy it centrally, locally, how you want. We will see in the architectures that come on the next slides. It's a rapid deployment, it's open source, low cost. And we spotted that the performance in private 5G networks of such audio and voice services remains insufficiently characterized. Therefore, with this paper, we addressed a gap. And shortly about the testbeds that we built, we have the one in Kaiserslautern, which is based on commercial software stack for RAN and core. And we have, in this case, a part of the communication platform, SIP and RTPEngine, that resides in the cloud. Everything is locally, so the UPF and the core are locally deployed. The testbed in Berlin, it's a bit more distributed. We wanted this on purpose. We have the RAN, of course, locally, but the UPF and the core are on a cloud server, and the SIP platform is on another cloud server, which it was the same use, so we used the same SIP platform deployment for both testbeds. So do not think it's a comparison between commercial and open source implementation software. It's not. It was not our intention. Our intention was to give an idea what kind of performances we can achieve with private 5G networks that already exist with their own architecture. We cannot compare the both because the architecture is different. The deployment sites of the keynotes are different. Just for orientation, we are working here with cloud servers, and they are located in Falkenstein, Germany, or in Nuremberg. And then we have the distance Berlin, Falkenstein, Berlin, Nuremberg, and then Kaiserslautern. Falkenstein, that comes of importance, is just an idea. We haven't accurately looked at the latency that they introduced.
You lost the microphone again.
I lost the microphone again. It's here. I think I have to put it better. Yeah. And let's look better on my computer. As I said, we have Maxware commercial implementation of a 5G RAN and core located on campus in Kaiserslautern. We have UEs that we realized with Latte Panda Delta 3. It's a single board computer, similar to Raspberry Pi, but it's more performant, and we paired it with the Quectel 5G modem to transform it in a UE, 5G UE. And on this computer, we run Ubuntu and Linphone for the over-the-top SIP app. We had Kamailio and RTPEngine on the public cloud, and after we conducted the experiment, we noticed that for the calls, the codecs that were chosen by Linphone were VP8 for video and Opus for audio. The others are details how the NAT was done. In this case, it was a bit special because all the phones got the same IP and port visible from the outside, but still the core worked. So, but this was nothing that we were able to touch. So these testbeds come with some constraints on infrastructure. We are not allowed to go at which level we wanted. So therefore, the architecture are different because we deal with integration here between two different research teams, two different universities, architectures, and so network architectures. And the testbed in Berlin is based only on open source stacks. srsRAN was chosen for this experiment, Open5GS, Kamailio and RTPEngine. We had to use WireGuard for the communication between the G-Node B and the core network to have SCTP over the public internet possible. And we used for UEs Nokia X30 smartphones, on which we run Linphone. And after placing the calls, we noticed that Linphone was choosing for a video the H.265 codec, and for audio the Opus. Yeah, a bit more details. We have the left half of the picture is the private 5G network without going into the details. We just show the UEs and how they are seen by the cloud server where Kamailio SIP server is running, and where we capture the traffic. And we highlighted here that, yeah, we got the same port for an IP, public IP for the UEs, but it was not an issue just for SIP grep that was discarding one of the RTP streams, but it was just a display issue. Actually, the call was going on correctly. The experimental methodology. So we had to launch 20 consecutive calls per testbed, each call 90 seconds. We did this for having a statistical meaning and making an average. The SIP RTP traffic was captured with srSRAN, SIP grep on the server running Kamailio and RTPEngine, and we define metrics, the call setup time, which is the time between the SIP invite and the 180 ringing SIP message. And for the quality of the calls, we were looking this time not simply at jitter and packet loss. We computed MOS, mean opinion score, which is actually a subjective metric, and we should evaluate this metric taking let's say 50, 100 persons listening to the calls and grading the quality from 1 to 5, 5 excellent. But we can avoid this time-consuming study using some mathematical models that ITU defined, and there is this G.1071.1 for evaluating the audio RTP streams, and there is another model also from ITU, G.1070, for evaluating video RTP streams. I'm not going to go into details what these models are. They are not easy to understand in a few minutes, but they are very well defined. You can find plenty of information. The main idea is that you can use them to have this metric that captures the quality of the calls. Yeah. So our results that we got, in the case of the testbed in Kaiserslautern, we got a call setup time of 0.17 seconds, and for TUB 0.45. Of course, they are different because TUB has to travel around Germany between the cloud servers. But the main takeaway here, both values are below the 3GPP ETSI call setup thresholds, far below. So we are doing wonderful. Just to remember, with some results we got 1 year earlier, when I presented last year here, we were comparing a bit voice over new radio and OTT, and I summarized these results. For example, in the previous paper, we had this local scenario and distributed scenario, where we had a local scenario means everything runs on a laptop, yeah? Quicker than this, I don't think it gets. And we had for OTT a call setup of 0.06 seconds. And then we distributed a bit. We put Kamailio and RTPEngine and the core in the cloud, and we got 0.09 seconds. with a cloud server that we chose, so the distance that we had at the time, which actually it was the same. It was to Nuremberg. And the last two setups are this from this year, RPTU and TUB, and we see that if we opt for a local UPF, but we had the entire core local, and the cloud Kamailio, okay, with a commercial stack for RAN and a commercial version of stack for RAN and core, we got 0.17 seconds, and for TUB we got 0.45. So just to have an idea how these values compare to each other. And then we went further to evaluate this MOS, mean opinion score, and we obtained for audio, for Opus codec, MOS of 4.01, which means consistently good. And for video, in the case of TUB testbed, because of this H.265 codec, we got a bit better value for 7.96, which means good to excellent, and for RPTU, not bad at all, 4.27, but with another codec, VP8, for video. And further, we were looking at MOS versus RTP packet loss, and we saw that, for example, even with a packet loss of 1% or 2%, H.265 stays stable. So the MOS was over 4.5. Just the summary of the results. We have the audio MOS, video MOS. We see a small difference. And then packet loss, cannot say we have too much loss there. Call setup time, yeah, as expected, there is a bit of a difference between the two test beds. And more than this, I think that was. The influence on quality of experience is actually given by the codec choice more than the network topology. No. No.
It's nice, right?
Ah, okay, wonderful. Where I was, here. So a few key insights. It's actually resuming what I've already said. H.265 consistently outperforms VP8 independent of testbed topology. The distributed TUB setup still delivers excellent video quality. Even with packet loss, yeah, we have good quality of the calls, good quality experience of users, and Opus holds MOS approximately 4 on both testbeds. So Opus proves to be quite a good, codec for this scenario, and also jitter and loss remain well within the real-time media thresholds. So main takeaways: C-based OTT voice consistently delivered high quality of experience. Call setup was under the thresholds that are set by 3GPP and ETSI. We avoided the IMS complexity, and yeah, the open source proved to work quite reliable, and it enables us to do experimenting, teaching, early stage innovation with good quality of experience and latency. As future work direction, we want to go deeper and go see under dynamic congestion what happens, under dynamic conditions what happens. For example, if we have congestion, if we have user mobility, if we have multi-user scaling, and see if we can assess the robustness of the private 5G networks. Under these conditions, we want to look also of integrating a kind of QoS, thinking on DSCP marking for priority traffic handling, to study the impact that this could be on the over-the-top services media quality. And we want to extend it to smart agriculture or other verticals campus to validate applicability. And now I'm going to close with several impressions. Photos from the conference and field trial, because we had a demonstrator last summer at the 6G conference in Berlin. This one are moving by themselves. So this is on the fields in Kaiserslautern. That was their network. It was it put on a van because they need to be mobile and have 5G access in the middle of nowhere for farming. And then the guys in Kaiserslautern are dealing with these AI-driven robots for smart agriculture. And then we said, okay, let's make it a bit smarter. Let's put a communication platform on top of it. And then if you don't have the specialist on site, you can connect instantly with specialists around the world. They can view how the crops look like. They can see the IoT sensors results, and they can immediately take actions. So the photos here are from the 6G conference in Berlin. We were visited also by the representatives of the federal ministry. Since we are funded by the Federal Ministry of Research, Technology and Space. And of course, all this work was possible with insight and expertise from Kamailio developers. And we thank you both for funding and for knowledge. And this was just a bit about our work. If there are any questions or during the coffee breaks, I'm happy.
Thank you, Ramona. Very useful. So let's see one quick question if someone it's up to it. Otherwise, we are quite late. We have Wolfgang until we have done preparing.
Yes, thanks for the presentation. A quick question. Do you have any figures about the end-to-end latency for audio, for instance? Because you just measured, I guess, the...
I didn't get it.
The latency for the audio. So the end-to-end latency of the audio path from one device to the other device.
No, only what I put. We haven't measured from device to device. No, we measure just the call setup time. It's problematic to measure on the on the UE. Okay, on the latte panda with Linphone, this is doable, but on the smartphone is not doable because we don't have access to the baseband and we don't see this traffic very easy. Also for the data bear, we could do it, but we haven't done. We stopped when we researched for the IMS and we couldn't get access to the baseband, and then we didn't come to the idea to measure this anymore. But it's a good point that we could take it for the next experiment.
Okay, thank you. You can find Ramona around the event.